Every program you've ever run, every game you've ever played, every file you've ever opened, all of it happens because of a single chip, the CPU. The CPU, or Central Processing Unit, is the brain of your computer, running billions of instructions every second, and without it, you'd be staring at a dead screen. At its core, the CPU has one main job: fetch instructions from memory, decode them, and execute them, over and over again at incredible speed. A single core handles one instruction at a time, but it works so fast, billions of cycles per second, that it feels instant. Modern CPUs contain multiple cores, each acting as its own mini processor, so they can handle several tasks in parallel. Some even use simultaneous multithreading, so each core can process multiple instruction streams or threads at once. The CPU talks to your RAM to grab data, coordinates with the GPU for graphics, works with storage drives, and processes inputs from devices like keyboards, mice, and controllers. Inside, the CPU is made up of several key parts: a control unit, which decides what instructions to run next and in what order; the arithmetic logic unit, ALU, which handles all the math and logic operations; registers, tiny ultra-fast memory slots for immediate data; cache memory, small but extremely fast storage inside the CPU for frequently used data; an instruction pipeline, which breaks tasks into stages so multiple instructions can run at once; and the branch predictor, which guesses what comes next to save time. A clever trick that's part of why the CPU is so fast, but also one reason why vulnerabilities like Spectre exist. A CPU's performance isn't just about clock speed, measured in gigahertz or billions of cycles per second. It also depends on IPC, instructions per clock, how much actual work gets done in each cycle. A CPU with a higher IPC can outperform a faster clocked chip if it's more efficient at processing instructions. A CPU starts as a wafer of pure silicon, etched with millions or even billions of microscopic transistors, using a process called photolithography. Those transistors act like switches, controlling the flow of electrical signals. They're arranged in layers, logic circuits, caches, control paths, all stacked and connected in a precise design only nanometers thick. The finished die is mounted onto substrate, packaged, and covered with a heat spreader to help with cooling. At such high speeds, CPU generates a lot of heat. To keep them stable, they're paired with cooling solutions, from simple air coolers to complex liquid loops. Without proper cooling, the CPU will throttle performance or shut down entirely to protect itself. Underneath the CPU are hundreds or thousands of delicate contacts connecting it to the motherboard. These come in different socket styles: PGA, with pins on the CPU itself; LGA, with pins in the socket; BGA, where the CPU is soldered directly to the board. This is why choosing the right motherboard for your CPU really matters. If the socket types don't match, they're literally incompatible. The pins are grouped by role. Power pins deliver voltage, ground pins complete circuits, data pins send and receive information, address pins tell RAM where to look, and control pins handle timing and command signals. If you bend a power pin, the system might still work, but bend a data or control pin, the whole system can fail. Intel's LGA design allows higher pin density and is more durable for frequent CPU swaps, but it's more expensive to manufacture. AMD still uses PGA for many CPUs to keep costs down, but switches to LGA for high-end Threadripper chips. Mobile devices often use BGA, permanently soldering the CPU into place to save space and cost. All CPUs speak a machine language called an instruction set architecture, which defines the commands the CPU can understand. On desktop, this is usually x86-64, also called x64, while many phones and tablets use ARM. x86 is the long-standing family name from older Intel processors, just means it's the modern 64-bit version of that family. ARM, on the other hand, is a completely different architecture designed for efficiency, making it ideal for mobile and compact devices where battery life matters. But yet, modern ARM chips can still pack a serious punch. The CPU only understands machine code, long strings of binary, ones and zeros. but writing programs that way is almost impossible for humans. That's where assembly language comes in. Assembly is a human-readable shorthand for those binary instructions. Instead of writing 1011000001, you can write move AL 0x61. It means the exact same thing to the CPU, but it's easier for humans to write, read, and debug. The assembler then translates this into binary code the CPU can understand and execute directly. Whilst the basic architecture is the same, CPUs are built differently depending on their job. Desktop CPUs balance speed and core count for general computing and gaming. Mobile CPUs prioritize low power use and heat efficiency for longer battery life. Server CPUs pack in more cores, larger caches, and advanced features for running huge workloads 24/7. Embedded CPUs are small, efficient chips built into devices like routers, cars, and industrial machines. Whether it's powering your phone, your gaming PC, or a massive cloud server, every CPU shares the same fundamental architecture, just scaled for the job. Understanding how it works, how it's built, and how it talks to the rest of your system is the first step in understanding how it can be pushed to its limits, or exploited. Thanks for watching, and if you enjoyed this, make sure you like and subscribe.